Today we finish up Chapter 13. I think we are finished, but I'll take questions. We get into Chapter 14, which starts to get into coding for bandwidth-limited channels. Here we're coding directly in terms of Euclidean space rather than in terms of Hamming space, and there's this wonderful quote from Neil Sloan: "Euclidean space coding is to Hamming space coding as classical music is to rock and roll." Meaning that in Euclidean space things are continuous, whereas we're discrete back in Hamming space. Nonetheless, there are strong connections between the two, which in 2 lectures I'll basically only have a chance to hint at. You were supposed to hand in problem set 9 last Friday, or today if you haven't already. Today we'll hand out the solutions for 9. And then Chapter 14 and its problems, which are problem set 10. These are not due. As always, I recommend you do them. Solutions will be handed out Wednesday. However, on the exam will not cover Chapter 14. All right, so everything we do this week is gravy. The exam is a week from tomorrow in the morning. Ashish will administer it because I won't be here. For this exam, it's closed book, except you're allowed to make 5 pages of notes, as you did 3 pages on the midterm. And I do recommend you bring a calculator, because one of the problems, the calculator will be helpful. And I was told that erasable memory should be cleared in the calculator. All right, so point of honor if you do that. Okay, any questions about the exam or Chapter 13? Yes?
So you're including the midterms that was also?
Yeah, everything in the course up to Chapter 13. The rule is everything that we covered in class. If we didn't cover it in class, then you're not responsible for it. Other questions? Okay, any last questions on Chapter 13? This was kind of the finale for binary codes. We found that at least on the binary erasure channel, we had techniques that would allow us to design LDPC codes that would get us as close to capacity as we liked, or at least I made that assertion, directed you to where you could find that done in the literature. And I further asserted that at least for binary symmetric input channels, like the binary additive white Gaussian noise channels, you could do much the same thing using techniques like density evolution or exit charts. Again, the issue is to design code such that this iterative decoding, after many, many, many iterations, will, with probability 1, converge to the correct solution, or with probability 1 minus epsilon. Okay, so that's a great conclusion to the story for binary codes, channels in which we want to have binary inputs. And way back in the beginning, we said that that was perfectly sufficient, really, for the general additive white Gaussian channel. When we were talking about binary code rates less than 1/2 or nominal spectral efficiencies less than 1 bit per second per hertz, which are equivalent statements. So what happens if we want to go over channels where we want to send at higher spectral efficiencies? We want to send 4 bits per second per hertz, as we certainly do over, say, telephone line channels, which are 3,000–4,000 hertz channels over which we want to send tens of thousands of bits per second. Or many radio channels will support high numbers of bits per second per hertz, and so forth. Well, obviously, you can't do that with binary codes. So today and Wednesday in this chapter, we very quickly, of course, go through the series of techniques that have been developed to go over bandwidth-limited channels, such as the bandwidth-limited additive white Gaussian noise channel. Clearly, you're going to need a non-binary constellation and somehow code on that constellation. But what you'll see is that both the techniques and much of the development are very reminiscent of the binary case. Historically, the binary case was always done first, and then the generalizations to non-binary followed. And so we'll see, you can start off with very simple hand-designed constellations, as we were doing back in the early chapters 4 and 5. We played around with little m=8 constellations and tried to optimize them from the point of view of, say, minimizing power for a fixed minimum distance between points in a certain number of dimensions in Euclidean space. Okay, now we want to go up to considerably longer constellations. So that was kind of at the level of, Hamming codes and single parity check codes and very elementary binary coding techniques like that. So we want more complicated codes, let's say moderate complexity codes. We will find things that are analogous to block codes, linear block codes, namely lattices. These are structures in Euclidean space that have the group property, as linear block codes do. And then we'll find trellis codes, which are the Euclidean space analog of convolutional codes. And basically our goal in the next 2 lectures is to get to the level of a union-bound estimate analysis of the performance of these kinds of coding techniques, which, like their binary analogs, sort of sit in a moderate complexity, pretty good performance, get up to 6 dB coding gain, can't get to capacity. All right, and so that's as far as we'll be able to go in Chapter 14. In the last page or 2 of Chapter 14, I briefly mentioned higher performance techniques, and it's generally accepted that you can get as close to capacity on these bandwidth limited channels, additive white Gaussian noise channels, as you can on the binary channels, in some cases just by adapting binary techniques in a kind of force-fit way, and others they're somewhat more principled, I might say. But in any case, by adapting the binary techniques, you can get turbo codes, low-density parity check codes, capacity approaching codes of various types for the bandwidth limited channel. But I just hint how that can be done in 1 page, and I can't include it in the course. Okay, so that's where we're going. So, basically, we're trying to design a constellation, set of signal points, constellation C or signal set or alphabet, script C if you like. And we're doing the kind of things we were doing back in Chapter 4 and 5. We're trying to, what are some of the things that are the parameters we have? We're going to do this in n-dimensional space. We're going to be concerned with the size of the constellation. The log of the size is the number of, log 2 of the size, the number of bits we can send. We call this M at one point. That will determine the number of bits we can send per n dimensions, or we can normalize it per 2 dimensions. Typically, I said in the bandwidth limited regime, we'll normalize everything per 2 dimensions. We're going to have an average power of the constellation, which I'm just going to write like that. We're going to have a minimum square distance between points in the constellation, which I'm going to write like that. And the idea is to kind of optimize the trade-off between this and this. Clearly, if I take a given constellation and I scale it up, I'm going to get better minimum square distance, but at the cost of increasing power. So I either fix the minimum square distance between points and try to minimize the power, the average energy over the centroids of a bunch of spheres, or vice versa. So when we do this, this is kind of the game. We get into a classical problem called sphere packing. If we say hold the minimum square distance constant, that means we want to have a certain minimum distance. Here I'll make it d min over 2. That means that there's going to be a sphere of radius d min over 2 around each point in this space, which must not be violated by the sphere of any other point. All right? So basically we're trying to pack spheres as closely together as we can. And we may be given the dimension. Here I have 2 dimensions to play with. We may be given the number m. In general now, we're going to be thinking of m becoming very large. We want to go to arbitrarily large number of bits per second per hertz. So think of schemes that will continue to work as we add more and more points. And if I do that in 2 dimensions, we'll get penny packing. You know, take a bunch of 7 pennies out of your pocket and try to squeeze them together as tightly as you can. It's effectively what we're trying to do. They maintain their fixed radius, and you'll get something that quickly starts to look like what this is called a hexagonal sphere packing, because the centers line up on a hexagonal grid. Okay, and in fact, I forget exactly what we did. We did some of these back in the early chapters, and let me draw a 16-point constellation, which I remember we did draw. All right, here's a constellation consisting of 16 pennies, and subject to my drawing ability, it's packed as closely as possible for a fixed minimum distance between the points. And as far as anyone knows, this constellation consisting of a set of points on a hexagonal grid is the most densely packed, most dense packing of 16 points in 2 dimensions as measured by the average power of the centers. All right? And it's not very symmetrical, but you can see it's based on a symmetrical packing. This hexagonal, this is basically a subset of 16 points from the hexagonal lattice. All right, if we extend these points in all directions, again, I haven't done it very well, but the hexagonal lattice is simply the underlying lattice here. Let me just draw a set of points. Look like this. I'm going to fail again. Sorry, I'm better at rock and roll than I am at classical music. Anyway, this is the lattice, and it's called hexagonal because if we draw the decision regions for this lattice, if we consider this as a set of points in a constellation and draw the decision regions, it looks like that. It's a little hexagon. Defined by the 6 nearest neighbors, they define 6 sides of a hexagon. And so each lattice point has a little region of space that belongs to it. You can think of its decision region. Okay. Now what makes this a lattice? All right, what's the definition of a lattice? Let's say an n-dimensional lattice. Very simple and elegant definition for a lattice. It's a discrete subset, that means a set of discrete points of Rn sitting in Euclidean n space that has the group property. And you now all remember what that means. It means if you, the group property under ordinary addition of vectors in Euclidean n space. Addition or subtraction, of course. So what are some of the implications of having the group property? That means that the sum of any 2 vectors is another vector in the lattice. does the lattice have to include the 0, the origin point? Anybody? Oh, good. I'm going to ask this on the final. Come on. Does it or doesn't it? It does. Why? Okay, that's one good answer. It has to be closed under addition and subtraction. Subtraction a point from itself is going to give you 0. More mathematically trained person would probably say, well, it obviously has to have an identity. Every group has an identity element. And that means if lambda is in the lattice, does minus lambda have to be in the lattice? Yeah, every element has to have an additive inverse, and so forth. All right? Well, so if I have a lattice like this, that means that one of these points has to be the origin. Say this one. Okay? Now, of course, you can have a translate of a lattice, and geometrically it has all the same properties as the lattice itself. Add any fixed t to all the lattice points. In other words, make the origin somewhere else. But that's not itself a group. That's the coset of a group. A translate is a coset operation. So lambda must be a group. And lambda plus t, any lambda translate, is a coset of lambda. All right, so most of the things you say about lambda are also true for lambda plus t, but in order to fix a group, we need the origin to be part of the points. Okay, if it's a group, what does that mean? That means if we take any particular point, say this one, regarded as a vector, then call this lambda 1, or let me call it G1 more suggestively. Does G1 plus G1 have to be in the group? Yes, so that forces this point to be in there, 2G1, 3G1, so forth. All of these have to be in there, as well as minus G1, minus 2G1, and so forth. Okay, so basically once we found a generator, all integers times that generator have to be in the lattice. So that means there's a cross-section along the axis defined by G1 such that these points are simply the integers scaled by whatever the norm of G1 is. Okay? And of course that holds for any of these neighbors here. We could take another, you want to look for nearest neighbors of zeros, take G2, and then of course all of its integer multiples have to be in the lattice. So we've got a set here that in some sense spans n space. If you took all, we have now two vectors, G1, G2, which are not linearly dependent. They're sitting in 2 space. So if we take all real linear combinations of these two vectors, we're going to get all of 2 space. If we take all integer linear combinations of these two vectors, they all must be in the lattice, right, by the group property. All right, we've already proved that all the integer multiples of either of them is in the lattice, so anything plus or minus those two. So certainly the lattice includes the set of all integer multiples of AIGI, I equals 1 to 2, where A1, A2 is in the 2-dimensional integer lattice Z squared. Okay. Could there be any other points? There actually could if you made a mistake and picked your initial vector to be 2G1, because then you wouldn't have taken account of G1. So you've got to take your 2 initial vectors to be 2 of the minimum norm points in the lattice. But if you do that, then you can easily prove that this is all of the lattice points. So in fact, a two-dimensional lattice is equal to a set of all integer linear combinations of two generators, which we can write as a little 2 by 2 generator matrix, G. Or very briefly, we can write lambda as G times Z squared, and we can view it as just some linear transformation of Z squared. So in this hexagonal lattice, we can view it as starting out with a square grid. Of course, Z squared itself is a lattice, right? Z squared is a group. All right, this is just the square lattice in 2 dimensions. We have Zn as a lattice in n dimensions in general. So I take Z squared, or Zn more generally, and I distort it. All right, I just run it through some G, which is linear transformation, and slants some of the generator points. And that's a general way of getting a lattice. That's not the way we usually visualize the hexagonal lattice. We usually visualize it in such a way as to recognize that it has 6-fold symmetry. But it's certainly a way to get it. And this has one interesting consequence. One of the measures we want for a lattice is the volume per lattice point. In here, the volume, you can divide this up into volumes that are all of equal size, and we can call that the volume of A2. This lattice, hexagonal lattice, is called A2. And it's the volume of that hexagon. All right, 1 over the volume of that hexagon is the density of points in 2 space, if you like. So density is 1 over volume. All right, so you can think of every point as having a unique volume, and if we basically consider the cells around each lattice point, they fill up 2 space with a perfect tessellation, tiling of 2 space. All right, these hexagons will, right? One easy consequence of the group property is that all the decision regions have to be congruent. In fact, just translates of one another by lattice points. The decision region around this point is the same as the decision region about 0, translated by a lattice point, namely the center of that decision region. I won't prove that, but it's true and easy to prove. Okay, so that's one way of finding what's the volume will mean the volume of 2 space per lattice point. But what's another way to do that? Another way is just to take this little parallelotope, whose volume is easier to calculate, and we can see that we can equally well tile 2 space with these little parallelograms, right? Just anchor, in this case, this is the one that's anchored in the lower left corner by the origin. Then we take another one that's anchored by this point. Take another one that's anchored by this point. Another one that's anchored by this point. And it's clear that that's another tiling of 2 space by regions, 1 for each lattice point, that completely fills 2 space with overlaps only on the boundary, which don't count. All right, so the volume of A2 is also the volume of that, what's called a fundamental parallelotope. And what's the volume of that fundamental parallelotope? Well, one way of calculating it is to take the volume of Z squared. If we can view this as a distortion of Z squared, which looks like this. All right, so if this is Z squared, what's the fundamental volume of Z squared? The volume of Z squared per lattice point. If this is 0, 1, minus 1, 1, so forth. 1, 1. What's the volume of Z squared per 1? Clearly, we have the decision region is this little square of side 1, or this parallelotope is also a little square of side 1. Its volume is 1. Okay. General geometric principle, if we take this and distort it by G, then what's the volume of, say, this parallelotope going to be? This parallelotope goes by G into this one, and its volume is the Jacobian, which is the determinant of G. So the volume of a lattice is the determinant of any generator matrix for that lattice. Just a nice little side fact. But it's an example of the kind of things you get in Euclidean space that you don't get in Hamming space. All right? Of course, there are various generator matrices that you could use to generate this lattice, but whichever one you choose, this is going to be true. All right, so this is an invariant among all the generating matrices. Okay, so that's a lattice. I haven't mentioned what's the most important thing for us about a lattice. A lattice is a group. What's a fundamental property of a group? Which I guess was embodied in the alternate set of axioms for the group. If I take the group plus any element of the group, what do I get? So the group again. Okay, let's interpret that geometrically. One of the nice things about this subject is you're constantly going back and forth between algebra and geometry. Geometrically, what does that mean? That means if we take this lattice, say the origin is here, and we shift it, say, so that the origin is up here, then nothing changes. Everything is invariant to this shift. All right? We can do this for any lattice point. That shows you that all the decision regions have to be congruent. It shows you that the number of nearest neighbors, the minimum distance from any point to its nearest neighbors is always the same for any lattice point. Basically, a lattice is geometrically uniform. That means you can stand on any of the points, and the world around you looks the same as if you stood on any of the other points. You know, think of these as stars in the universe. And somebody blindfolds you and drops you on one of these points. Can you tell which one of those points you've been dropped on if nobody's written anything on these points? No, you can't tell. The world looks the same from whichever one you drop on. So that means the minimum squared distance from any point is the same as every other. So the number of nearest neighbors at minimum squared distance is the same. It means the total distance profile starting from any point is the same. It means if we were to take one of these points and send it over a Gaussian channel from a very large set, and we take one of the points from the interior and send it over a Gaussian, added white Gaussian noise channel, the probability of error is going to be the same regardless of which point we send it from, because the probability of error is the probability of falling outside your decision region. All right, and since the decision region always has the same shape, it's invariant to which point you send. So this geometrical uniformity property, which that's the general name for it and has all these specific consequences that I just listed, is the principal property of geometrical property of a lattice. Okay, it just follows from its group property. You don't have to be a lattice to have this property. For instance, the translate of a lattice is not a group, technically, but it obviously has the same geometrical uniformity property. And there are more elaborate examples of things that look less like lattices that are nonetheless geometrically uniform. On the other hand, lattices definitely are geometrically uniform. So this seems to be a good thing to do, because what's our objective? We're trying to have d min squared be the same for every point in our constellation. We want to pack these pennies as close together as we can. That means we want to hold d min squared constant for every point we're going to use. And so lattices have that property. So it seems like a good way to do sphere packing. And in fact, sphere packing is in n dimensions is a very old mathematical subject. You know, how How many spheres can you pack around a 3-sphere? Is it 12 or 13? That was debated in the 18th and 19th centuries, and I think it's only finally just been resolved a few years ago. This turns out to be not an easy problem. The densest sphere packing in 4 dimensions was found in the mid-19th century. In 8 dimensions, I think around the turn of the 20th century. In 16 dimensions, it's the Barnes wall lattice, which we'll see a little later, which was found in 54, about the same time as Reed-Muller codes, or maybe it was 59, maybe a little later than Reed-Muller codes. The Leech lattice was certainly found in a little earlier than that, but around the same time as the Golay code, to which it's a very close cousin, and so forth. So, you know, you might think that these questions had all been settled, but in fact they're still open for most specific dimensions n. Conway and Sloan have the authoritative book on this, which basically lists what we know about the densest sphere packings in all dimensions. So here's our idea. Our idea is we're going to go consult the mathematicians and find out what the densest sphere packings that they found are in various dimensions. In 2 dimensions, it's the hexagonal lattice. In 1 dimension, it's the integer. And basically, the integers are the only packing with regularity properties in 1 dimension. In 2 dimensions, you could consider z squared, or you can consider A2. These are the 2 obvious candidates, the square and the hexagonal packings. In 3 dimensions, you get face-centered cubic packing in the, what's the BCC? The base-centered cubic packing, I guess. Say again? Body-centered, thank you. I'm sure you're right. So anyway, there's some things that are known about this from classical mathematics and current mathematics. All right, so what our idea is we're going to try to find the densest possible lattice in n dimensions. But for digital communications, for coding, we only want a finite number of points from that constellation, right? So what we're going to do is we're going to create our constellation based on a lattice and on a region of n space. And the idea is simple. We're just going to intersect the lattice, or maybe let me allow a translate of the lattice, with the region. And make this a finite compact region. And this will give us a certain finite subset of the points in the lattice. Okay? And when I draw a constellation like this one of size 16, that's what I've done. I've basically taken A2, or it's actually a translate of A2. I think the origin is in here somewhere. And I draw a sphere around the origin. And I take the 16 points that happen to fall within that sphere. And I call that my constellation. All right, so that's the idea in general. Think of the region R as a cookie cutter. All right, we're going to take the cookie cutter and chop out a finite number of points from this nice, regular, infinite grid. And that will give us a constellation. All right, so we'll be able, especially for large constellations, we'll be able to make some approximations that will allow us to analyze that kind of constellation very easily. And this, actually, the best constellations we know are of this type. Another, we've taken as baseline MPAM. Well, what's MPAM? We take the lattice plus t, let's say, to be z plus 1/2. Okay? So that means we don't take the origin, but we take points 1/2, minus 1/2, 3/2. They're equally spaced points, but we've shifted them so as to be symmetric about the origin. 5/2, minus, minus, so forth. So this is z plus 1/2 is our lattice. And then if we want 4 PAM, we take a cookie cutter consisting of this region. All right, so this is the region going from -2 to 2. It's not unreasonable to expect that if we take a region of length 4, we're going to get 4 points. All right? If again, it's symmetric around the corner, because each of these points takes up about 1 unit of space over here. All right? So if we made it from -4 to +4, we have a region of length 8, and we get 8 points. So forth. Okay? So that's how we do MPAM, and then scale it if we want to, but this is the basic idea. Similarly for M by M QAM, like everything else, it's just doing the same thing independently in 2 dimensions. Here we take our lattice to be z plus 1/2 squared, which is just the offset z squared, offset so as to be symmetrical to 4-way rotations, 90-degree rotations. So here is z squared plus 1/2, 1/2. Okay, and then again, here to get 16 QAM, for instance, we might take the region to be -2 squared, which again has area 16. Each of these, you might think of this as just taking the little square around each of these. Each of these squares has area 1. So when we take the union of all those squares, we get the region. That's another way of characterizing this region. It's just the union of all the decision regions of the points that we want. If you started from the points, you could certainly invent a region that is the union of those decision regions. It would have an area equal to the number of points times the volume of 2 space per each point. Okay, that's the kind of approximation we're going to use. That the bounding region is clearly going to have something like the number of points in the constellation times the fundamental volume as its volume. All right. Okay, so this is our idea. This is what we're going to call a lattice constellation, and we're going to investigate the properties of lattice constellations. Not the most general thing we could think of, but good enough. Seem to have the right sort of property. And we're going to take it at least as far as the union-bound estimate, so we can get a good estimate of probability of error if we take one of these constellations, like M by M QAM, and use it to transmit over a Gaussian noise channel. And furthermore, for large constellations, meaning as we get well up into the bandwidth-limited regions, large nominal spectral densities, we're going to be able to separate the analysis into lattice properties and region properties. Lattice properties and region properties. And we'll basically be able to just add these up to get the overall analysis. All right. By making some judicious approximations that become exact in the large constellation limit. All right, so let's now restrict ourselves to lattices or translates of lattices and start to analyze them. What are their key parameters? For our application, which is digital communications. Well, one is the minimum square distance between lattice points. We've seen that doesn't depend on the particular point. So this is the minimum square distance from any lattice point. The number of nearest neighbors. The volume per lattice point. And is there anything else? Seems to me there's a fourth one. No. Guess that's all we need to know. So I want to combine these into a key figure of merit for coding. Again, we did this back in we did this back in chapter 4 for a complete constellation. We found a figure of merit by holding the average power fixed for a fixed number of points m and a fixed dimension n, and maximizing the minimum square distance, or conversely holding the minimum square distance fixed and minimizing the average power. So we get some figure of merit that was kind of normalized, and we could just optimize that one thing. The key figure of merit was called by 19th century mathematician Hermite's parameter, but we are going to call it the nominal coding gain, because that's what it's going to turn out to be. And it's just defined as follows. The nominal coding gain of a lattice is just this minimum squared distance, so it goes up as the minimum squared distance. But then we want to normalize this, and the obvious thing to normalize it by, we want something that's going to scale as a two-dimensional quantity. If the lattice was scaled by alpha, then this would go up as alpha squared. So we want something that will scale in the same way, and what we choose to normalize it by is the volume of lambda per 2 dimensions, if you like. So you can see immediately this is invariant to scaling, that the nominal coding gain of lambda is the same as the nominal coding gain of alpha lambda. Is alpha lambda a lattice, by the way? If lambda is a group and we have any scale factor alpha greater than 0, then alpha times lambda is also a group. Everything's just multiplied by alpha. So alpha lambda is a lattice, and this is actually one of the homework problems. If you scale everything by alpha, d min squared goes up by alpha squared. The volume goes up by alpha to the n for an n-dimensional lattice. But when we take 2 over n, we're going to get back to alpha squared. So alpha c of lambda is alpha c of alpha lambda. So this is what you want. You want a kind of scale-free version of a lattice, because obviously when we use this, we're going to feel free to amplify it or compress it any way we want, as we do with QAM. All right, so this is normalized in that way. We prove on the homework it's also invariant to other things. If you took say, an orthogonal transformation of this lattice, a rotation, reflection, multiply it by a matrix that doesn't change the scale, think of it geometrically as an orthogonal transformation, is that going to be a lattice? It is going to be a lattice. Everything is just going to, we just have some h out here times g z squared, and that's still of the form of a lattice. Or call it u for orthogonal, unitary. So we multiply it by some orthogonal matrix u. It's still a lattice. If we look in here, orthogonal transformations don't change square distances. They're not going to change this, doesn't matter. And actually, they might. No, it's a rigid rotation. I'm sorry. Everything here stays the same. Hexagonal lattice still is hexagonal lattice because it's a rigid rotation or reflection geometrically. And the volume clearly stays the same. So none of these things changes. And orthogonal transformation isn't going to change this quantity either. So we can rotate this or do whatever. And then finally, there's an even more interesting one, which is if we take the lattice lambda to the m. This is simply the Cartesian product. It's the set of all lambda 1, lambda 2, lambda m such that each of these lambda k is in lambda. All right, so it's the set of all m tuples of elements of lambda. This clearly lives in dimension mn, so it's a much higher dimensional lattice. You know, simplest case is z to the m. It lives in m dimensions, whereas z is down in one dimension. So it lives in dimension mn. It's a way of constructing high-dimensional lattices from low-dimensional lattices. It's something that in communications we consider to be almost a non-event. Sending a sequence of elements of lambda is the same as sending a sequence of elements of lambda m, right? Okay. In fact, if we just send a sequence of things from here and a sequence of things from lambda, there's no difference from a receiver's point of view. So we regard these two lattices as equivalent from a communications point of view. Well, what happens to d min squared? D min squared doesn't change because we can always, d min squared is, by the way, the weight of the smallest, I should have said that. D min squared is equal, you can always do things relative to 0. D min squared, therefore, is the squared norm or energy of, it's the lowest squared energy of any non-zero lattice point, same as we did with Hamming codes, just by the group property. K-min is the number of such lowest Euclidean weight points. Okay, here, what's the lowest weight point? It would look something like this, where this is one of the lowest weight points in lambda. So d min squared doesn't change. This changes, but we're not considering that. The volume, what is the volume? It turns out that, not hard to show, that v of lambda to the m is v of lambda to the m. And therefore, you can show that this figure of merit doesn't change, even if you take Cartesian products. All right. So, for instance, it shows that the nominal coding gain of z to the m is equal to the nominal coding gain of z, which is what, by the way? I should have done this as the first example. What's the minimum square distance of z? 1. What's the volume of z? 1. So this is 1. Or 0 dB. We're going to measure nominal coding gain in dB, which is, well, we're getting us into communications. What's the nominal coding gain of the hexagonal lattice? By asking this question, I'm basically asking, is the hexagonal lattice denser than z squared in 2 dimensions, than the square lattice in 2 dimensions? And if so, quantitatively, how much denser is it? Okay, well, there's a root 3 in it, but that isn't exactly the answer, I don't think. Okay, there are various ways that you can do it, but one of the ways is to take as a generator matrix 1, 0, 1/2 root 3 over 2. You like that as a generator matrix for the, that's taking this and this as the two generators and recognizing this is 1/2 and this is root 3 over 2. That makes the length of this equal to 1/4 plus 3/4 equals 1. Square root is 1. So these are my two generators of length 1 in a hexagonal lattice of minimum square distance 1. So based on that, I can say that the volume of A2 is what? Root 3 over 2. Not hard to take the determinant of that, right? What's the minimum square distance in this scaling? What's the minimum non-zero weight? Squared norm, it's 1. So this is equal to 1 over root 3 over 2, which is equal to 2 over root 3, which is equal to what? This is 3 dB, This is 4.8 dB roughly. Square root is 2.4 dB. So this is about 0.6 dB. That's where it pays to be facile with dBs. This area, by the way, if you tried to compute the area of this little hexagon here, what would it be? If the area of this parallelotope is square root of 3 over 2, what's the area of this hexagon? The same, right? They're both space-filling when centered on lattice points. All right? So they have to have the same area. All right? So that's an easy way of computing the area of a hexagon. This particular hexagon, anyway. But you would get the same result in either way. So comparing this with z squared, I now have a quantitative measure of how much denser A2 is than z squared. Put in one way, if I fix the minimum square distance of each of them to be 1, if I'm doing penny packing and I say I want pennies of a certain radius to be packed in two-dimensional space, then this is 1 over the volume, which is basically the density. The density of A2 is 2 over root 3 times as great as the density of points in z squared. I get more points per unit area with the same distance between them using A2 than I can with z squared. So that's the significance of this parameter. So it's an obvious thing for Hermite to come up with. It's going to turn out to be equally fundamental for us. Okay, so that may be all we want to do on lattices for the time being. Yeah, seems to be. All right, so we're talking about lattice constellations. The other thing we have to develop is the properties of regions. So let me talk about regions. I'm thinking of a compact region in an n-dimensional space. So again, let me fix the dimension to n, and we're going to have a certain volume. That's obviously an important characteristic of a region, and I'm going to assume this is finite. And what's the other thing that we basically want? Well, when I pick a constellation like this by intersecting a lattice with a region, eventually I'm going to let the points in this constellation be equiprobable, as I always do in digital communications. 16 points, say they all have probability 1/16, the uniform probability over the discrete points. One of the approximations I'm going to make, so what's the average power of that constellation? We could figure it out by taking 1/16 times the energy. I should say the average energy. I'm sorry, we're not talking power here. We're talking energy, but I read it as P. What's the average energy? It's 1/16 times the L2 norm of each of these points. All right, if you like that, simply the Euclidean squared norm. All right, and we get some average. But here's the key approximation principle. I'm going to say the average power of this constellation, especially as the constellations get large, is simply going to be approximated as the average energy over this bounding of a uniform distribution over this bounding region. You know, suppose I simply put a uniform continuous distribution over this circle, the sphere, two-sphere that I've used to be my cookie cutter. I'm going to say that's going to be a good approximation to the average energy of these 16 discrete points, which are, by construction, they're spread uniformly over this region. The approximation is I'm kind of approximating a unit impulse of weight there by a distributed weight across its, well, actually across its whole little region. If we have a hexagon around each one, uniform distribution over the hexagon. And if that's a reasonable approximation, then it's reasonable to say the average power of the whole constellation is just the average power of a uniform distribution over this region. Okay? It's good exercise to try it for some moderate-sized cases, and you'll find it is a very good approximation. In any case, it's the one we're going to use. So the other key parameter is going to be P of R, which is, in words, the average energy of uniform distribution over R. Sorry, script R. Now, when we write this out, this actually gets a little formidable, so I think it's better to remember what we're actually trying to compute. Oh, and one last thing, we're going to normalize it per dimension. So what do I mean? What's a uniform distribution over R? This is P of X equals 1 over the volume of R for X in R and 0 otherwise. Right? Uniform within, 0 outside. And what does it have to equal? It has to be equal 1 over V of R, because its integral has to be equal to 1 if it's a probability distribution. So to compute P of R, we basically take the integral from over R of this probability distribution, 1 over V of R, times what? The energy per dimension. The total energy of X is X squared, L2 norm of X. Normalized per dimension, we're going to put an n over there, dx. Okay, so that's an equation for what it is I want to compute. Okay? I think it's much harder to remember the terms in this than to remember this verbal description of what we want. But you may be more literate than I. Okay, now let's define, we want a normalized quantity comparable to Hermite or coding gain over here. The normalized quantity we're going to use, we want to take P of R, and what should we normalize it by to make it scale invariant, let's say, again. Again, if I take the region, I scale the region by alpha, get alpha R. What's going to happen to the average energy of a uniform distribution over R? It's going to go up as alpha squared, right? Energy scarce goes as the square of the scale factor. So again, I want to normalize it by V of R over 2 to the n. Okay, because this is also something that will go up as alpha squared if I scale alpha by R, scale R by alpha. Okay, so this is what's known as the dimensionless or normalized, has both names, second moment. Another name for this is the second moment per dimension of the uniform distribution over R. This is a normalized or dimensionless second moment. think I call it normalized in the notes, but it's always called G in the literature. And let me just introduce here, well, what's the normalized second moment of an interval? Say a symmetric interval around the origin. G to the minus 1 to the 1, which is like the interval that we use to pull out the MPAM signal structure. So let's take R to be n to be equal to 1, R just to be the interval from minus 1 to plus 1. Then V of R equals what? It's the length of R, which is 2. Okay? What's P of R? The integral from minus 1 to 1, x squared dx, which is 2/3, right? I think so. Right, 1 over 2. Thank you. It's 1/3. All right, so what is G of R going to be? G going to be, this is going to be P of R over V of R squared. And so this is going to be 1/3 over 4, or 1/12. Okay, that's not as nice as this over here, but it is what it is. All right. This is a number that shows up in quantization, for instance. Uniform scalar quantizer, you'll find a 112 in there. Why? It's because of this equation. Okay. If we ask again about the invariances of this is the last homework problem for this week. It's invariant not only to scaling, but again, it's invariant to orthogonal transformations, because orthogonal transformations won't affect either of these things. A rigid rotation won't, about the origin, won't affect V of R or P of R. And furthermore, it's invariant to Cartesian products. Again, if we just have a series of regions, a region made up basically is the Cartesian product, like an n cube, is a Cartesian product. We just pick each of the dimensions independently from some set R. Then that's not going to affect the normalized second moment either. Exercise for the student. So from that result, I can say that G of minus 1, 1 to the m, which is what? This is an m cube of side 2. All right, just pick each of the, if I say each of the coordinates, x1, x2, x3, up to xm, it's got to be xk in minus 1, 1. Then what I'm going to get, the region defined by that, is an m cubed centered on the origin of side 2. Okay? So the normalized second moment of that is going to be 1/12. Okay? This is where the shortcut begins to help you. I guess I'm trying to put too much on one board, but the last thing I want to put up on here is the shaping gain, or the shape gain of a region. Is defined as the shaping gain of the region is equal to 1/12. So we're kind of taking as a baseline the m cube in any number of dimensions n over G of the region. In other words, how much less is the dimensionless second moment, the normalized second moment, than what you would get for an n cube? In every dimension, except for one, a sphere is going to be a better region from a second moment point of view than an M cube. M cube has corners. Really, it's pretty obvious that if you want to minimize the normalized second moment in any number of dimensions, you would choose an M sphere. Because if you have any wrinkle that comes out of an M sphere, anything that's not an M sphere, you should try to squash it back in it, and that'll make it an M sphere. You'll take higher energy and make it lower energy for the same little unit of Play-Doh or mass stuff. So a sphere will give you the best normalized second moment in any number of dimensions n, so you're always going to get a g of r that's less than 1/12. That's good. And this measures the amount of gain. Again, you can measure this in dB. It's going to translate directly to dB. I suppose I could do an example for the sphere in 2 dimensions, but I won't. How are we doing on time? Okay. Let me see if I can do the union-bound estimate. That would be a trick, but I think it's doable. Because this is where we're going. So, the union-bound estimate. Which is something we did way back in Chapter 5 or something. Is basically we're given a constellation, which we're going to have a lattice constellation based on some lattice lambda and some region. So this is like our M by M QAM, or it might be this guy, which is better than 16 QAM in some sense, in 2 senses, actually. The union-bound estimate, what is it? Probability of error is approximately equal to, let me do it per block, so I'll have the number of nearest neighbors per block of our constellation times q to the square root of d min squared of our constellation over, what is it, 4 sigma squared? Four sigma squared. Okay. And you remember how we got this. We took the union bound, we took all the pairwise error probabilities, and from that we get contributions from KD at every KD contributions at distance D. We added them all up in the union bound. We said, well, for moderate complexity and performance, at least this is going to be dominated by the minimum distance. So this is the minimum distance term. This is the number of minimum distance terms, and this is the the pairwise error probability we get for each minimum distance term. Okay. Now to compute this, I'm going to use 3 approximations, but 2 important ones. This continuous approximation that I've already referred to. First I'm going to say that the average power of my constellation is approximately equal to just this second moment of R. The average energy per dimension of R. And then I'm going to say, furthermore, how many points are there in the constellation? This will affect what rate I can go at. the average number of points in the constellation, also mention this, is going to be approximately equal to simply the volume of my bounding region, V of r, over the volume taken up by each point in my lattice. Okay, that makes sense, doesn't it? What I want to do here to get 16 points is I take a sphere whose area is roughly 16 times the area of one of these little hexagons or one of these little parallelograms, and I'll get about 16 points because that's the density of it. And there's a final little approximation, which is that I'm going to assume that we're somewhere in the interior of the lattice, so that the average number of nearest neighbors in the constellation is simply equal to the average number, to the number of nearest neighbors in the lattice. So that's a reasonable approximation. That's a very obvious one. If I take any constellation based on the hexagonal lattice, for a large enough constellation, the average number of nearest neighbors is going to be 6. If I take it on the square lattice, the average number of nearest neighbors is going to be 4. All right, but we know we're not terribly interested in that point, that either. Okay, then let me do a little manipulation here. I'm going to write this as Q of d min squared of C, which is going to, clearly I'm going to also assume that d min squared of C is equal to d min squared of the lattice. So I'll make that d min squared of the lattice. And I want to normalize that by V of lambda to the 2 over n, whatever dimension n I'm in, to get something that we're familiar with. So I need a V of n over 2 to the n. And anticipating a little, I'm going to put a V of r over 2 to the n. And then over here, I'm going to put V of r over, just going to come out right, V of r over 2 to the n over, this seems upside down. So no, it isn't upside down. Because I'm using this expression here. I do want 1 over g of r. So this is 1 over g of r. If I multiply this by 1/12, I get 1 over g of r, so I need to put a 1/12 here. And then I have a p of r over 4 sigma squared. So does everyone agree I can write it that way? All right. This will be good. Go out with a bang. Okay. So what are all these things? This is the coding gain of lambda. This, according to this, is the size of the constellation to the 2 over n, approximately. The rate of the constellation is log 2 times the size of lambda r. So the rate is equal to just log 2 of this quantity. So I can say 2 to the r. This is 2 to the r equals this. So this would be 2 to the 2 over n, 2r over n. Is that right? Again, I'm unsure if that's what I want. This is the shaping gain of the region, these three things together, times 3 times what's P of R over sigma squared? That's the SNR. That's the average power per dimension, and this is the average noise power per dimension. So I've used up these in that. So I've got a 1 over 1/12, that's 12 times that. So this is 3 times SNR. And let's see, this is 2R over N is just 2 to the...
Is that just 2R? Because rate is normalized by the dimension.
Yeah. And furthermore, it's minus, because it's upside down, so it's 2 to the minus 2R. Actually, what I want is the spectral efficiency. And the spectral efficiency is the rate per 2 dimensions. So this is just 2 to the minus rho. Okay? So with a little help from my friends, what's SNR over 2 to the rho? It's approximately SNR norm. Certainly true as rho becomes large. It's actually SNR over 2 to the rho minus 1. So this is SNR norm. Okay, so with a little hand waving and a few high SNR approximations, we get that, in summary, for the UBE, the probability of error is approximately K min of lambda times Q to the square root of the coding gain of the lattice, the shaping gain of the region, times 3 SNR norm. And that's a wonderful approximation. Let me just call out some of its properties to you, and then we'll talk about them next time. But first of all, there's nothing here that all these terms involve either lambda or R. All right, so we have completely separated in this analysis the effects of the region from the effects of the lattice. We can choose the lattice and the region independently, and they independently affect how good a performance we get. For the baseline, which was either MPAM or M by M QAM, we have, for the baseline PAM or QAM, we've set it up so that both the coding gain of the lattice and the shaping gain of the region are equal to 1. So for the baseline, this gives us what we already developed back in the early stages. I won't worry about this. Q hat, but it does give you the right coefficient out here too, depending on whether you normalize it per 2 dimensions or what. It just gives you Q to the square root of 3 SNR norm, which I hope you remember from chapter 5. So this was our baseline curve for MPAM or M by M QAM. We just plotted versus SNR norm the probability of error per 2 dimensions, which is what I recommended, and we got some curve. All right, so this is the baseline. And now we've got everything separated out in a nice way, so that if somebody gives us a lattice with a certain coding gain and a region with a certain shaping gain, those both just add up as gains. If that's all we had, forget the coefficient, we would just move to the right here They would give us effective reductions in required SNR norm by the coding gain of the lattice and the shaping gain of the region. Okay, and we'd get the same curve moved out over here. Again, as in the binary case, typically we're going to get a larger number of near neighbors, leading to a larger coefficient out here. We want to normalize this per 2 dimensions. Per 2 dimensions, it's only 4 for the baseline, but in general, we're going to get a Ks of lambda, the number of nearest neighbors per 2 dimensions, which is going to raise this a little, and that will lower the effective coding gain down here. But we've basically, by these large constellation, high SNR approximations, we've really reduced the analysis of lattice constellations to a very simple task. Just analyze what's the coding gain, what's the shaping gain, number of nearest neighbors, plot the performance curve. End of story. Okay? So we'll start there next time.